Thank you so much, Justin. I really appreciate it. Yeah, so thank you also to everyone for coming out today. I really appreciate it. And I'm happy to be here and sharing some of the work we've done on quantifying geomorphic change using drone-based lidar. And one of my goals for today is I hope this can be kind of broadly accessible across disciplines. So if there's any questions that come up, please feel free to put them in the chat and we'll get to them at the end. But as all works probably should, I have to start off by acknowledging moving my video. I have to acknowledge some of the people who've contributed to this. So first off, Doctors Brian Unitas and Doug Edmonds, Doug's my supervisor, are the professors in charge kind of the drone-based LiDAR project here. Then myself in the bottom left, and then Steve Scott down there. And the four of us, he's our pilot without whom none of this would be possible. And the four of us are kind of the day-to-day operations crew nowadays. Quinn Lewis, who was a postdoc, now is at U Waterloo, was foundational in setting all this up. I'm also going to be showing some of the work and interpretations from Dr. Ed Herman, and we've also had contributions in there from Eduardo and Tyler Doan. So to get started, geomorphology is the science of scenery. I mean, it's all about landscapes. It's the surface of the earth, how it changes shape over time, and the processes that drive that change. We're interested in studying these for a variety of reasons, but it's one thing to imagine studying these landscapes here in this kind of barren landscape, but what do you do when there's trees in the way? How does vegetation affect our understanding of the Earth's surface? That's kind of going to be a motivation for today's talk. But why do we want to understand the shape of the surface of the Earth? And I often use the word topography here. And topography could just be the shape, but I like to think of it as the elevation. It's the z-axis, right? So for every spot on Earth, how high off the ground, or how high is it? And it's useful across disciplines, right? From habitat modeling, where you have ecological niches at different elevations. If you want to track how sediment and water are moved through the landscape, or for predicting ancient deposits, it's critical. There are archaeological implications, atmospheric through deflecting weather systems, and of course, tectonics and hazards, and many more. So if we agree it's important to understand the surface of the Earth, today I want to talk about first how we currently do it. I want to pitch drone-based LiDAR as a new innovative way of measuring that surface. And I want to talk a bit about how it fits into those existing methods and where I think it's best used. And then I'm going to demonstrate some practical applications through our work to help illustrate some of those advantages. So the first thing I'll say is existing methods. It may be a little surprising, maybe not, that most modern topographic methods don't actually resolve the Earth's bare surface. And when I say bare surface, I again mean without vegetation. This includes photogrammetry, so structure from motion, which is very popular nowadays with the consumer drone revolution, and radar, SRTM, that resolves tree tops. So it's an important distinction here that we can have different quantitative representations of the shape of the Earth's surface, depending on whether we're looking at the dirt or the trees. As a quick example, here's a satellite image from Southwest Montana. And I think that we can get a lot more understanding here if we look at the LiDAR for this area. And without the presence of trees in the way, we can pretty immediately see this kind of sublinear feature, this surface running from the northwest to the southeast. And that's actually the 1959 Hebgen Lake earthquake. That's a fault scarp from where the surface of the Earth was displaced. And that we can't get from photogrammetry because there's trees in the way. So I've been saying LiDAR a bunch. What is LiDAR? Well, it's light detection and ranging. So if you have any familiarity with sonar, that's sound detection and ranging. Radar is radio detection and ranging. The concept is pretty much the same. You emit some kind of signal, it goes through space, bounces off an object, and is received. And if you know the speed at which that signal moves through the air or a medium, you can solve for the distance. The LiDAR operates on the electromagnetic spectrum, just like radar. Radar operates kind of on that centimeter to kilometer scale, each individual wave. On the other hand, LiDAR is a very, very, very narrow band right around the micron size. So potentially a lot of energy and high resolution. The two most common ways to collect LiDAR data now are terrestrial, where you set up a tripod, for example, in the woods here, It spins around and shoots lasers in every direction it can see, measures the distance to all those points. Or airborne, where you attach it to the bottom of a plane and fly and scan the landscape. I argue that those two exist on opposite ends of a spectrum, where terrestrial LiDAR, you have a pretty small spatial extent that you could scan, everything within eyesight of a tripod, some meters off the ground, but a very high point density, and the cost per scan is very low to operate. Airborne, on the other hand, you can collect very, very large areas at a pretty lower point density, 1 to 10 meters points per meter squared, which might be good in your application. But the biggest issue is the cost. It's $10,000 at least for a scan. And from what I've been hearing lately, the cost of hiring aircraft is only going up. So that's kind of a limitation of what kind of questions you can answer. When I say that LiDAR can see through vegetation, what do I really mean? What's the physics of that? Well, as a basic understanding, when you shoot a pulse, a laser, you can imagine it as just a ton of photons all getting shot out, and some of them will make it all the way to the ground, and those will return. We call it the last return, the bare earth return, but many will get interrupted along the way. And so it might bounce off of a leaf at some point, a branch at some point. And again, the wavelength is very small, so you're not diffusing and scattering it the same way you would with some other methods. But what that means is when we split those out, if we just look at all the returns or just those first returns, or just, if you had 4 returns, the important thing to recognize here is that a single pulse can have multiple points in space that are resolved, up to several returns, which 4 are shown here. This is kind of cool in 2D, but I think you really don't get the point until you see it in 3D. We get the treetop elevation, sure. We get the forest floor elevation, and we get everything in between. This is the value of having multiple points per return. This has been revolutionary across many fields. And I think that one of the greatest aspects of this revolution is how open the data is, generally speaking. You can go to Open Topography. I just took a screenshot. Every time I show this to someone, I have to make a new screenshot because the area of LiDAR coverage is growing. Everywhere you see a green block there, you can download LiDAR. And one thing I love too is it's designed to be relatively accessible. So if you have the technical ability to operate a GIS software like QGIS or ARC, if you can download and open a raster, you can effectively access these data for whatever your research purpose is. And LiDAR is not static. It's been improving over time. And I think a lot of this is due to a lot of research and development dollars in the automotive field. They've really been pushing to try and get LiDAR units to be lighter, operate faster, and be more energy efficient. And that's an important one. And what that has actually allowed is that now you can put LiDAR on a drone. I'll never get tired of that. So I see drone-based LiDAR as filling a gap in these two different end members of LiDAR, right? So with a drone, you get all right, aerial coverage, depending on your research question, about that square kilometer scale is a good scale. You get about an order of magnitude higher point density than airborne, but I think the real improvement is the cost per scan is so much lower. Instead of $10,000, it's gas money to get Steve and I to the field and back. So the operating cost gets a lot lower, which adds to the number of questions that you could answer. So the third option, as I mentioned, we have, this is our specific model. It was created by Phoenix Designed. 2018 is when we got it. It has redundant GPS to about 3 centimeter accuracy. We also use a base station to do differential GPS for processing. And it's got real-time kinematic to talk to the ground for just pathfinding. It has an onboard IMU, which basically means it has a very good understanding of its aspect at all times, its roll, pitch, and yaw. And then in terms of data collection, we have a LiDAR unit, a pretty standard camera, and a hyperspectral camera. Now, to get a little more in the weeds, a little nerdier on the data side and the hardware side, for raw collection, it can fire 100,000 pulses per second. And each of those pulses, as I mentioned, can have up to 5 returns. We also have true color photos from the digital camera and the hyperspec. And I should mention that the current, the successor to the laser scanner we have on our drone. So the current model, not 2018, but 22, has 300,000 pulses per second and a full spectrum or full waveform return. So instead of returning just discrete points, it can return the whole waveform. Typical flight takes 6 batteries, each is about a laptop battery, and that gets you about 10 to 13 minutes of data collection, plus a couple minutes of start and end for calibration, takeoff, and landing. Typical flight has about 20 million points in the point cloud, a couple hundred raw photos, and our biggest day so far, we've collected about 2 square kilometers. And for processing, we use some proprietary software in order to classify which points are on the ground versus vegetation. Other users also use it for building. There's a lot of architectural and industrial users of drone-based lidar. And we create a bare earth model from that. So this is a point cloud from a site we scanned where you can see, first of all, the thing to know is so the first thing, there's a river that goes from the top of the screen that flows down towards your bottom right. We can also see a road that runs from the left to the right, some power lines, which is incredible if you think about a drone flying through the air, shooting a laser, having some of those photons bounce off of a wire and make it back to the sensor. And the color here, the color on each of these dots is actually intensity. So how much energy the photon had when it made it back to the sensor. So things that are more reflective are brighter. So for example, the reflective strips painted on the highway show up in bright. If we take a cross section just along this highway, we're going to look at this from the side, almost like an X-ray. We can see underneath the bridge, which from a remote sensing perspective is incredible. And if you look at the trees, you can see the boughs, the trunks, the leaf structure, which ones are reflective, which ones aren't, the species differentiation. I think any particularly motivated forestry ecologist could really make use of this, calculating biomass, for example. So as we go on to the applications now, the first project I want to talk about is understanding hill slope processes. So how do hills move sediment? How do they get the shape they have and change it over time? And whether or not there's a forest there, how do the trees actually affect that? Do they slow it down, speed it up? Well, the answer is we're not entirely clear because we don't really understand the shape of hill slopes on certain scales, at least. We lack quality topographic data. To illustrate the importance of data quality, if we look about an hour, here's a site about an hour southeast of Bloomington, where we are, and we're going to look at the same place with 4 different types of data. First is SRTM, which is radar, about 30 meter pixels, and it's tough to see what we're looking at. At the 10 meter NED data set, we're starting to be able to resolve, okay, we can get the shape of the land at least. The Indiana statewide LiDAR, and Indiana has shot statewide LiDAR twice right now, which is very, very cool. It's about 1 meter pixel, and we can get some pretty interesting features, but when we go down to our 1/4 meter pixel with the drone that we collected, we can see footpaths. I mean, think about the vertical resolution, think about the vertical displacement of a footpath and the fact that we're observing it, right? And it really matters for the research questions that we have. So, for example, if we're trying to figure out, all right, we have a slope here, we can see it's high on one side, sloping down the other, there's a gully in there, but what is that noise going on inside the square? Is that real? Is it not? Along that cross section that's drawn there, is that data processing? Well, when we switch from the 1 meter to the 25 centimeter, we can see, no, those bumps are actually real. In fact, other than the overall slope, maybe the primary roughness element here, the main feature that you can see moved around are these pits and mounds paired up. And it's kind of curious, what is this? But of course, we can go out to the field, and they are trees that have fallen over. It's called tree throw. So a tree gets knocked over, usually by wind. It brings the dirt from its root ball up into the air, moves about a meter or 2 to the side, and then as the tree decomposes, it leaves behind a mound. And Tyler Doan has done some interesting modeling work showing that maybe 10% of all the sediment that gets moved down these hill slopes gets moved by tree throws. So I guess it goes without saying then that if a tree does fall over in the woods, you can see it with a drone. You can use lasers. But it's when we can see it, when we can map it, that's when we unlock new questions, right? The spatial distribution has so much information in it. So in this area here, you can see each black dot is a tree throw. And you can start noticing there's almost none right at the top of these hills, and there's almost none at the bottom. And this is from Tyler's paper. You can see there's actually a pretty tight distribution without going too deep in the details. These occur over pretty narrow ranges of topographic variances, which is roughness, and slopes. So there's a preferential slope here control. And aspect is another big control. These things preferentially occur on east-facing slopes, which is super cool because here winds are usually from the west, especially the fastest winds that probably do the work of knocking down the trees. So we here have found data through this roughness that suggests that it's easier to blow a tree down when you're pushing it downhill than pushing it up here. And that leaves a signature in the landscape, which is super cool. And it's worth considering that if we wanted to repeat this with one of the other LiDAR techniques, right? Airborne, we've established, doesn't have the spatial resolution. Terrestrial absolutely does, but how many times would you have to set up a tripod and calibrate it and collect data, move it, do it again to measure all these? There's 600 points. I mean, if you knew where they were, I guess maybe 600 collections. We did this in about 3/4 of a day. So collecting the data was very cool. So that's one advantage, the higher spatial resolution, including in vegetated areas. So the second example I want to give, this is one chapter from my dissertation, is studying outbreak floods or outburst floods. It's basically any kind of flood where you suddenly have water released from behind a wall. They're relatively uncommon, but have a disproportionate impact on the surface of the earth now and in the rock record. They're difficult to predict, so it's hard to study. And if you want to understand the landscape impacts of an event, you need to know what it looked like beforehand, and you don't always have that. So in 2020, in May, 2 dams catastrophically failed in central Michigan, causing the evacuation of over 10,000 people during the COVID-19 pandemic. In addition to the human impacts, we were interested in learning about what a large flood does to a landscape. And this is particularly relevant because there's over 91,000 dams in the US. The average age is 57. Many of those have a high hazard potential, which means if they were to fail, they would cause a significant amount of infrastructure and human damage. And many of them are ranked as deficient. So it's unfortunately important to understand what the geomorphic effects are going to be downstream of these failures. Our study site took us to central Michigan, specifically the towns of Edenville and Sanford. That's where the 2 dams that failed were. And this is kind of unique among a lot of these studies in that this failure was actually captured on film. So you can see the full dam to the right. It's not quite overtopped.
There it goes. There it goes.
And then the earthen dam fails. And if you take a look at the landscape to the side, it's treed, grassy, and
there we go. There's the rush.
There's the rush. So keep an idea in your mind of what that landscape looked like, because here we're going to look at a satellite image from a few years before. You're going to see the lake that was created by the dam in the top half of the image. The dam itself is in the bottom half. Some features around that you could look at. There's a marina here, a bunch of lakefront property, and then the dam, well, one of the generating stations itself and where the failure occurred. And so where we saw that video was in that grassy part in the lowermost of the 3 boxes. And then I'm going to skip forward to after the flood, where the lake is essentially gone. The marina is now hundreds of meters away from water, as are the riverfront, lakefront properties, and the dam itself has failed. We had the state of Michigan collected 2016 statewide LiDAR. And so far we went up 3 weeks after the flood, 3 months after the flood, and 1 year after the flood, because we were interested in absolutely the changes to the landscape from the flood itself, but also how does the system evolve over years? Does most of the change happen right away? Is this a relaxation kind of thing? So if we zoom in kind of up near where the break happened and immediately downstream, this is where the treed area was washed away and became a river. We can calculate the change just from the initial flood and find multiple meters of vertical change, incision, deposition. We can map this out and start studying the landscape effects. And what's cool is because we also did the field work and the photography, we can relate some of these features we see. For example, the upstream, that forested area is now scoured down to glacial till, or the scours in the downstream where trees have been washed away. Looking again kind of right at where the break was, this is a point cloud straight out of the lidar that hasn't been classified. And you can see, again, the breach where the dam used to be and the power lines. And it's worth mentioning here that we are unable to resolve through water in almost all situations. That's generally, broadly speaking, true for LiDAR. There are certain ones that have certain wavelengths and energies that can resolve through water, and we can get a little bit of bathymetry if it's very clear and still, but generally speaking, it gets you the surface water elevation. This is a little bit downstream where you can see a dam failed. So we have, this is a little bit downstream. You can see there's a point bar here, which is treed beforehand. And then when we flew the drone, you can see the trees have been knocked down in the downstream direction. And the force of the flood was great enough to strip the leaves off the upstream side, which we can see. And we worked with a local farmer who owns some of this land to establish and quantify how much soil he had lost to help him with his with his interactions with FEMA and other organizations. The second town that experienced damage was Sanford. This town was positioned right beneath the dam, and there's a very nice little municipal park area, a small business district, some residential housing. And unfortunately, when the flood occurred, the town was almost completely submerged. And when the water went away, it left behind sand. We got up there again about 3 weeks later, and this was one of the more impactful comparisons, I think, that I saw at least. And beyond just the human element, scientifically, I mean, it brings to mind questions. Okay, well, was this erosion? Was this deposition? Are there spatial patterns? How do we prepare? Should we shore up certain areas in the future? And I think that these questions, we can begin to answer them when we can measure bed forms in left outfield, right? This is perishable data that's valuable for calibrating future models and understanding these patterns. This work is actually a paper. It's the subject of a manuscript that I have in review at Geology right now with Doug and Brian and Dr. Nathan Naomi up at U Michigan. So there's a value to rapid response deployment, and you can collect perishable data at a high spatial resolution. Finally, I'm going to go into something that's kind of near and dear to my heart. This has been an ongoing project that Quinn started 5 years ago, and I've been doing for about 4 years because I'm coming up at the end of my PhD. This is about understanding the small scale mechanics of how rivers meander. So what do I mean by that? Well, this is a 30-year time lapse of satellite imagery of the Mamoré River. And meandering is common, but not well understood. And what I mean by that is we understand that as a general simplification, that erosion happens on the outstream bank, the cut bank, and deposition happens on the instream bank, the point bar. And then when those two processes happen, that allows the river to move laterally, scroll across landscapes to create illustrations like this. But the individual actions that cause that erosion, that cause that deposition, how does the erosion at the cut bank happen and deposition on the point bar? Is it per flood? Is there some relationship? Those questions we haven't been able to answer as well because we lack high temporal resolution. And when I say temporal resolution, what I mean is if spatial resolution is how closely you can look, temporal resolution is how often you can look. And I believe it's limited because of the cost of airborne LiDAR. As an example, this is a really good paper in our field answering just the question I pitched: how does the meandering and how does the erosion and deposition take place? And so I just drew a grid here. You see the year on the x-axis increasing to the right, stage height on the y-axis, that just basically means water level above some datum. We can plot the stage gauge from the USGS over time. So each of those spikes is a flood that went through. And then if we look at when they collected data, it's great. But the issue is, if each flood is doing its own action on the point bar, we can't really resolve the changes associated with a single flood, right? We're smoothing, we're integrating over a bunch of change. I think drone-based LiDAR allows us an opportunity to improve on that. So we picked as a field site the White River in Indiana. It's one of the sites of some of the early works on meander development. And you can see some oxbows here. You know, it's quite typical in farmland, but once you reveal it with LiDAR, there's this beautiful richness, this complexity to the floodplain. Even a boring Midwest meandering river has a lot of information to hide if you can understand the topography very well. This is my particular bank. It's near Worthington, Indiana. It's about an hour west of me. And if we highlight the banks here, I want to show you how much it meanders in 20 years. So I'm going to skip forward, and it moved about 130 meters. That's about one bank full width. So about 6.5 meters per year. So think of you're standing on a cut bank and you go back to that exact same position in space 1 year later, the riverbank is going to be 20 feet behind you. And now you're standing in air over the river. This thing is moving very quickly. We're going to focus on just this point bar here in cut bank. And I'm going to do the same resolution experiment here where we discuss the importance. And what we're going to do is look at it with SRTM first, the 30-meter pixel. And it's tough to see what's going on. The National Elevation Data Set at least tells us that there's a river here. Airborne gets us down to the 1-meter scale, and drone-based LiDAR, we can get down to 25 centimeter. And I'll totally agree that at this scale, it's tough to see the difference between the airborne and drone, right? Do we really need it? To get a better illustration of that, I pulled up this figure here. And the first thing I'll say is just in the bottom right of your screen, you'll see there's an inlay, an inset here that's going to be on all the slides, and it's going to show you where we've zoomed into for context. But looking at this point bar again on the left, we have a treed upper third, kind of a shrubby, grassy middle third, and then the bare sand as the lower third. And if we look at this through airborne LiDAR, we remove the vegetation and we can start seeing furrows and ridges, right? We can start seeing bar scale features. It's pretty cool. But when we get down to the 25 centimeter, we can see bed forms. It's things that previously looked like noise are now clearly signal. And we'll get back to those bed forms a little bit, but I want to talk about the temporal resolution, not just the spatial. So for temporal, again, created this graph of river level over time. We could pick some arbitrary point on the point bar, some elevation, and say, well, how often did the river get deep enough to submerge that part? We can plot the stage gauge data, again, courtesy of the USGS. And these are the 21 scans that Steve and I have collected to date. And Quinn, the scans we've collected to date. We can do things like look at one specific individual scan, and we could pull it up and see, what does this landscape look like? And for the fluvial folks in the room, I'll point out, you can see bar lateral accretion sets, or accretion surfaces rather, packages. You can see bed form trains on the surface itself. And then we can do things like, I'm going to skip 1 year forward in time, and it's kind of radically different. It's much different. And it's a little tough to see just skipping back and forth, but what we can do is subtract one time step from the other to measure how that change happened, right? So a place that's the same elevation in both scans has a change of 0. Something that's been lowered will have a value of negative the amount of the change. That's what I did here. The color here is such that white or gray is no change. Red is erosion and blue is deposition. So you can see most of the grassy and vegetated part didn't have much change, but on the point bar surface itself, there was a lot of erosion going on and some deposition on the downstream end, which It's maybe a little bit weird for a point bar, but very cool. We can also keep looking and find just interesting things. So this feature showed up on the point bar one day and looks a bit weird and kind of like a strange jellyfish. We go, is that real? Well, we can compare it to the field and see, yeah, there was a log jam. A big flood came through and it stranded a bunch of trees on the point bar. And that caused deflection of the flow, right? It caused scouring upstream. There's a turbulent wake behind that allows deposition and erosion to occur in a special pattern. And then if we skip just 3-4 months later, a couple floods later, it's gone. The wood, of course, but also the topographic memory, the evidence it was ever there. And if we calculate that change, you can see everything that was high has been eroded. Everything that was low has been filled in on the scale of meter. At least it's 50 centimeters shown here, but greater in some locations. That's kind of temporal resolution we can't get if we're just scanning once every couple of years, right? And as an extreme example, these two scans were taken 3 weeks apart with just one small flood in between. And we still see on the order of about 50 centimeters of erosion. So these surfaces are dynamic in a way we didn't appreciate before because we weren't looking often enough. Cut banks are much the same story. This is just the other half, just a little bit downwards of where we were before, and I've blanked out the point bar just to make it easier, less distracting. This cut bank, the flow is coming out of the screen and erosion's going to the left, and it kind of gets eroded by this crumbling behavior where scoops or bites are taken out of it, slumping. I put the timeline back up at the top, and if I go ahead now and just highlight the bank just so we can see where it is during the first scan, I'm going to skip forward 1 year. We can see how much the riverbank has moved and where it's moved and where it hasn't moved, which is kind of cool too, right? There's some locations where there's been almost no erosion and others where there's been considerable amounts. And if I not fast forward, but if I just scan through a number more steps through time, over the 4 years, we've had about 25 meters of cut bank erosion. And what we can do with this temporal resolution, again, how often we look is understand, is this a planing? Is this spatially located? There's a lot of interesting questions. Just a little bit to the left of where we were before. This is part of the floodplain, the cut bank, and there's some interesting features that I liked here. This kind of ridge, halo kind of looking feature here. That's actually sand that gets deposited during overbank floods. It's pushed through the vegetation into these streak lines, and it's kind of a levee building process in a way. A little bit further downstream, we have these kind of vertical streaks, diagonal streaks in the floodplain that are a bit confusing until you go after a flood and see they're caused by trees that get dragged over the landscape, leaving these, I'd almost call them tool marks if this were glacial. And this one's a little more esoteric, but I love it. This is the upper point bar. So this is above where we were looking before. This is what we call a chute channel. So the river, this is only wet when it's flooding, but the river is essentially trying to cut itself off and make a new oxbow lake, right? It's trying to make a shortcut. So flow is to the bottom right. And if we look at this area down here, there's a little delta that's growing onto the point bar, which is so cool. And what I love is we can follow it through time and we can see it grow. We can see it redistribute its sediment. It can bifurcate. It splits into ridges. It does all the things that deltas are supposed to do, but on a point bar. And it's worth highlighting at this point that evolution we just watched was happening under a forest. Without lidar, we wouldn't know it was there, much less be able to map its evolution over time. So the temporal resolution, I think temporal resolution is important for a lot of research questions because of the lower cost per flight. And then finally, this is some work that has been done by some folks, especially at Herman, on understanding some more archaeological and anthropological work on some earthworks at Angel Mounds. So Angel Mounds is a site in Indiana, which was originally constructed by indigenous people about between 1000 and 1450. It's quite a large site and has 11 human-made mounds, so earthen structures. And it was excavated in the 1800s, but especially in the 1900s. So this is what it looks like from the air. And it's Mississippian culture. It's about that age. But one thing I point out is if you look at the topographic map in the top right, that's it. You can get some information on that. You can see the mounds, but I think we can do a bit better in topography. And so that's one of the mounds. Why do we study these? Well, when you can calculate and measure the volume of a mound, it gives you some pretty interesting anthropological evidence. So if you have a very large mound, there's two ways you can get that. If it's built in a short time, that means there were a lot of people working on it who had a lot of free time. Otherwise, you could also have a group of dedicated people who worked for generations and generations, but a smaller population. One thing I could say is based on some of the dating we have, one of these mounds was created in essentially geologically an instant. So years to decades, implying a pretty large population and a lot of investment in a particular location. From more of the conservation side, a lot of damage was done to these mounds by original excavation efforts, 1800s and early 1900s in unethical ways, right? Destructive excavation, looting essentially. But, we're still now, they're still experiencing damage from natural causes, right? Just land slumping as any hill slope might. And we're able to see that when we weren't before because of this high precision imaging. Do we need drone-based LiDAR here? Well, I put up here the statewide on the left and drone-based on the right. In both, you can absolutely still make out the mound. There's no discussion there. But if you look at the statewide on the left, and I just highlighted one area, you see there's a lot of vertical lines, and they might be noise, they might not. It's tough to see. In the drone-based, most of the noisy vertical lines are gone, but some of them stuck around and actually pop out even better. And if you look elsewhere in the image, you can find more examples of that. And that's because there are genuinely subtle topographic lineaments in this landscape. And those are very important for understanding the lives of the people who once lived here. Through this, we're able to, it's essentially a great way to map out where you want to do future work. And we've been able to discover, or not we, but the folks working here have been able to discover archery towers, stockades, really interesting stuff about the alignment of these mounds to cosmic stars. In addition, one thing I'll draw your attention to that I thought was particularly cool were these odd zigzags in the bottom right there, and then that square feature inside the red circle. At first, I thought, are these data processing errors? But no. Through this, they decided to shoot geomagnetic surveys over that area and discovered those are legitimate lineaments and actually foundations of houses. It was the border of housing blocks, roads, essentially, alleys, which is very, very, very important for informing future ethical excavations, where the anthropological goal of understanding the lives of the people without disturbing the human remains and honoring the wishes of the current descendants of those tribes. So, for example, these folks, the culture typically buried ancestor remains in homes. So it becomes very important to know where those homes are so we know where not to dig. So it's just a overall useful tool for getting a lay of the land. And I just wanted to highlight here that those lineaments are not visible from the ground. Even if you know you're there, they're very challenging to see. They're centimeter scale vertical features. So coming up towards the end, a couple takeaways I hope to have come across. Drone-based LiDAR is an emerging field, and I don't necessarily say it's the answer to everything, but I like to say that it allows us to ask new questions. I think that topography, it's worth thinking about measuring it at both spatial resolution, absolutely, but temporal resolution too. How often you look is sometimes as important as how closely you look. And this has really emphasized to me the importance of topography and in uniting different disciplines, right? There are so many different fields that could benefit from understanding the shape of the surface of the earth. And with that, I'd like to end the talk. And thank you so much for listening and for having me here. Happy to answer questions. If some reason we don't get to it, or if you're watching the recording, feel free to email me. You can tweet at me at avulstcanuck, or you can go to my website at harrison.studies.rocks. Thank you so much for your time.
Wonderful. Thanks so much, Harrison. It was a fabulous presentation, and we've got a boatload of questions that have come in. So I will start working through these. The first question kind of gets at some of the fundamental physics of how LiDAR works. And Doug asks, how does the recording sensor in the LiDAR system know which laser pulse corresponds to which return?
I think the simple answer there would be just it's timing, right? It's kind of like in seismic, where you listen for the first return, the second return, the third, where the faster the return occurs, the closer the object is. And I guess what it does is it just listens for the reception of how many photons it's getting back, and then it identifies peaks and assumes those are discrete events. What I'll say is that it's a bit tough to know for sure, because we're still at a point where a lot of the processing that goes on is proprietary. It's done under the hood. It's done in black boxes, for lack of a better term. We're at a point now where LiDAR manufacturers have, I believe this is true, I was told it, so I'm going to repeat it, that they have proprietary wavelet shapes, waveforms, that they think are best able to really distinguish between which pulse is which return.
Interesting stuff. Thank you for the clarification on that. We had a couple questions come in about the system that you were using. If you could comment on kind of the drone model and the LiDAR sensors that you used as part of this, the results that you shared today.
Absolutely. Unfortunately, I don't have a slide for that, but I'm happy to go off the top of my head and just say it out loud. And feel free to email me and I'll give you a more specific spec sheet. But I could tell you we fly a Matrice M600 by DJI. That's the specific drone model we used. And I see there's some questions about cost. So I can say when we bought it, again, it was purchased right before I got here, but off the top of my head, I think the Matrice was about $8,000, give or take. The most expensive component was absolutely the LiDAR unit itself. That one was a Phoenix Mini Ranger. I believe now they're on the Mini Ranger 3, but we were on Mini Ranger 1. I believe that's what it was. And that was, I think, about 70, 80,000. I think that's the most expensive component by far. And then there's GPS that's necessary. There's some other features, but I think those are the real big costs and the most important components and models. Everything else I think is pretty interchangeable.
Yeah, I'm glad you brought up cost, because yeah, a couple of our questioners had asked about that, and James had asked as well, kind of some of the operation and maintenance costs. So, do you have a full-time employee in charge of it, for like your pilot, or just for calibrating and kind of yearly maintenance costs? Maybe you could speak a bit to those.
Absolutely. And sorry, I feel rude looking away from the camera, but my co-authors are helping me out a little bit here. The people who hold the purse strings and get to sign the checks, I just get to use it. I'm being told the cost is about $180,000 total without the hyperspec for, I believe, everything. I don't know if that includes training and people, but yes, it does include training and people, and it's a Regal LiDAR sensor, Minivux, that was it.
Okay.
So, yeah, with a full-time employee, we don't have a full-time employee. Well, that's not a lie. So we're very, very fortunate here that there's a field and instrument scientist, Steve Scott, who I mentioned, who is our pilot and also does a lot of the work on yearly maintenance and calibration and setup, and we're really indebted to him. This isn't the only thing he does. He also has other duties within our department and other departments. So yearly maintenance, it's not too bad. I think batteries are the big cost, because they have a limited lifespan, on the order of probably a year or two. You have to buy a new set. I think that covers most of it. But I guess the point I want to make here is that the upfront capital expenditure, absolutely, it's large. It's larger than a Phoenix. It's larger than a Phantom, but the operating cost is much lower because once we have it, I mean, it also I should also mention it takes about a day's work to post process the data, and that's mostly done by grad students or whoever wants the data the most.
We had a couple questions that came in about permitting. Did you have to get a special permit in order to do your drone LiDAR survey, and how does that all work typically?
Oh, this is a fun one. Okay, so first things first, in order to fly the drone, I can say just US, and based on my understanding, in the US, you have to get a part 10 something. Point is, like, there's a special license you have to have in order to fly a drone for research purposes if it's more than half a pound, which ours is. So that's necessary. In terms of permitting, it is very, very site specific. So my understanding is that the biggest, and don't legally quote me on this, but my understanding is that the biggest thing is getting permission from where you take off and land. So we mostly work with private landowners. That's what we did for part of the work up in Michigan. We worked with the local farmer, Bill Bacon. In Worthington, we have permission from the local municipal city and landowner. I believe we had to interact with some of the officials and engineering sites and companies up in Michigan in order to get permission to take off and land from their sites, just so we can get the best angle. Because one of the big constraints is that you have to maintain line of sight with the drone at all points during the flight. So that does bring some complications. In fact, one time we brought a cherry picker out so that Steve could go up in it when he was flying, so he could always see above the trees, see where the drone is.
We had a few other questions come in about kind of the height of the survey, like how high you're flying when you're taking these data. And I don't know if some additional questions too about accuracy in terms of the vertical and horizontal scales. Maybe you could comment on that as well.
Totally. It's it's really something. So we fly about, I think, 60 meters above ground is kind of our standard, but it's possible to vary. I mean, there is a trade-off between elevation, flight speed, and point density, right? As you can imagine, flying lower to the ground and flying slower collects more points per square meter, but higher is going to be, cover more area at a lower density. I think that the highest topography, because I saw one question about that, the steep landscape, we've gone up to 80 meters that was specifically Brian working in Montana. So they've done some pretty steep terrains out there, and it's possible as long as you maintain line of sight. In terms of resolution, I'd say that, I should also mention that the way we navigate those steep slopes is that the drone actually follows topography. So it maintains a constant elevation above the ground. So if the ground goes down, so does the drone. And as the ground comes back up, so does the drone. It's just part of the flight planning software. It's kind of built in, and we use a software called Lychee. In terms of resolution, the way we're able to get such good spatial resolution, again, with any sensing, with any sensor, you need to know exactly where the sensor is in space, right? You don't know its exact position, its angle, because otherwise it's not too meaningful to know how far away something is relatively. We do that through differential GPS. So we have a base station that's set up for 2 hours on site. So we do that instead of fixed ground control points.
Okay, that was another question people were asking about ground control points.
So instead of fixed ground control points, which are challenging in some areas, we set up a base station. We use that, and then we know the position of the base station accurately because we collect for at least 2 hours and then submit to the Opus, the online positioning user service, I believe run by NOAA. As long as you have 2 hours of continuously recording stationary GPS data, they can use their own differential base stations, usually I think on cell towers, in order to calibrate further, which blows my mind. It's just differential on differential and differential. But I'll say that we tested this in Michigan when we did repeat surveys over paved areas. And the magnitude of error there was, so the magnitude was probably on that 10 centimeter scale.
This is vertical or horizontal or both?
Vertical. But the but it's pretty normally distributed. And what I will say, well, okay, it's not actually 10. That's in both directions. What I really mean to say is that what we can do is do alignments later. So if you have a fiducial area, what you can do is take a flat surface in two different scans and align them together. And that gets you down to centimeter scale, vertical. It's the point cloud is normally distributed about within a centimeter or two up and down at that point. It's pretty fun.
I'm a little bit, well, more than a little bit unfamiliar with the lidar sensor itself. Does it have settings where you can kind of dial in the accuracy that you're using? And I assume you have it turned all the way up, or like how does that play into this question of accuracy and resolution?
Right. My understanding is that it definitely has a fixed wavelength. It's stuck at 950 nanometers. 905? It's stuck at about that many nanometers. It also has a fixed pulse rate and spin rate, but the way that we would actually change our resolution if we wanted to is, again, just in the flight planning. How high we fly, how low we fly, how fast and slow. One of the important things that we do is in almost all of our flights, for every area, we'll actually fly it twice perpendicular. So if one flight is grids of up and down or north and south oriented, we'll fly it again oriented east and west. And that does two things. One is that in our software that does the corrections, and the software is Terra Match and Terra Scan by Terra Solid, Finnish company. What it does is it allows you to essentially compare matched paired points between the two different flights and align them to reduce some of your internal error. That's a big part of it. And the other thing that does is it allows you, especially in vegetated areas, you want to get as many oblique angles as possible, right? You can imagine that if you're approaching an overhanging tree, might be, a branch or a hill might be pretty tough to see from shadows in one direction, but if you're coming at it from another direction, you have a better chance.
You mentioned previously that the software, you're able to program in kind of a constant survey height. And I think you said, was it 60 meters or something like that? That is roughly about the height you put in.
Roughly,
is it the same thing with regards to the velocity of the drone as it's flying these routes? You have a fixed speed and it maintains that throughout the survey?
Yeah, absolutely. I definitely say that when we got the when we got this software and service, it was a little bit, I'd say, Wild West in terms of it works, but it's not entirely sure why each different component works. But, we follow the best practices, and some of those include straight lines as much as possible, very gentle curves, throw away the data that are collected while you're turning, keep the speed constant as much as you can. And these are all things just to try and eke out every little bit of accuracy you can. But definitely in our software, we establish a minimum and maximum speed, and takeoff and landings are done manually. But once you're actually doing data collection, that's all pre-programmed with someone watching very closely.
And I would imagine that I think you've said this previously, that there are trade-offs there too. So the lower and slower you fly, the more points you can collect, and the higher the accuracy you're able to achieve.
Absolutely, because it works on a push broom system. And what that means is if the drone's flying this way, then the lidar is actually scanning in a 360-degree circle perpendicular to the direction of flight. Now, it's a bit weird with the hands, but if you trust me, it's a spinning circle. And so you can imagine it's only scanning the ground half the time, and it's collecting 100,000 pulses per second. But if you slow down, then each of those areas can be, the lines are closer together, right? To the point that we did one particular flight in Cincinnati. It was a fairly vegetated area in a small area. And the research question was more ecology based, I guess. It was looking at some invasive species in the river. And for that, we did an experiment. We flew low, slow, and overlapping a ton of times. And we ended up getting to the point of about 500 points per square meter in a vegetated area, which, I think the limitation is kind of how long we want to spend doing it.
Yeah. A few additional questions here before we wrap up. Daniel wrote in to ask about, I think you mentioned for the archaeological site that they had done some geomagnetic surveys of the zigzags, and he was asking if those were done via drone as well, or if that was surface-based.
I believe surface-based. I wasn't there for those, but I believe surface-based. I think it was kind of conventional. And I think the real benefit there to the folks doing that work was being able to cite it, kind of knowing where to look, right? Because 400, with that large of an area, you can't scan everything. So it's kind of, all right, let's try and high grade where we go.
It's maybe sticking with the archaeological theme. Ellen had a question wondering about kind of permissions and permitting. And I know we talked a little bit about that already for just in general your survey sites, but were there any specific challenges that you experienced when working at archaeological sites, and how did you navigate that?
Yeah, unfortunately, I'm going to have to pass that one off. I'm not too much the expert. I think the individual to contact on that is Ed Herman. Okay. And I will say, Ed sent me a message. Turns out the geomag was done by drone. So what do I know?
Okay, awesome.
Yeah.
Great. There was a question here about Will wrote in to ask about photogrammetry and wondering how that compared to lidar in terms of cost and resolution.
Absolutely. Sorry, I will go back for one step. I will say that it was about the administrative side of working on archaeological sites.
Oh yeah, sure.
Right. Sorry, I just had another thought on that. I'd say that in everything that we do, and especially everything that Ed does, I believe everything is done in consultation with extant tribal representatives of modern Native American groups, both those that are still in Indiana and those whose ancestors previously might have stayed here in Indiana and then later been displaced further west. So I think a lot of that has close work with tribes, and it's but I'm just not sure too much about like, oh, is there certain conservatory government bills and that stuff? I'm not sure about that, but I can just speak to that human aspect. And then yes, sorry.
Sorry, I was just going to repeat the photogrammetry question about how that compares to lidar in terms of cost and resolution.
Perfect. In my opinion, if you are looking to study, if you're looking at a landscape that's already barren, right? If you're looking at a landscape that doesn't have vegetation, I think photogrammetry can get you very good results. If you have good control points, you take enough photos, you give enough processing power, you can get photogrammetry that approaches the resolution, the spatial resolution of lidar at a fraction of the cost. Off the top of my head, I think nowadays a Phantom is a couple grand, right? And you might even be able to get cheaper, and you could probably do decent photogrammetry with pretty inexpensive drones, small ones that you might not even have a license for, right? If it's less than half a pound. But I think the real difference here and the reason that we needed the lidar was because of vegetation. We need to be able to see through. Sure. So it's probably 2 orders of magnitude more expensive to do it with drone-based lidar. But there are some research questions that photogrammetry can do almost as well. And there are some applications that you really need the lidar. And I will say with photogrammetry, your resolution is really limited by your picture resolution, right? If you have your phone right off the ground and you're taking pictures of a pile of rocks, you can get some pretty good results.
Sure. Maybe just a few additional questions here.
Thank you so much for asking. This is fun.
Question about the time length from the drone lidar survey to a 3D model of the surface. So for instance, could you follow a pattern of interest in real time if you were constantly going out and doing surveys? Like how quickly can you turn that around into a digital model?
That is fun. I like that. Well, what I would say is that, let me just stop that. So if you want a nice DEM, then it will take probably a day of processing. If all you want is just a couple pictures, you get some data that comes in the software. It gives you points in real time, but they're really not great in terms of, sorry, I'm rambling a bit. It's not very satisfying. You can see points come in, but honestly, the real problem is that if we're collecting 20 million points in the air over a 10-minute data collection flight, let's say, that amount of data is probably a couple hundred megabytes. And the drone is only connected to the computer that actually manages the lidar software intermittently. It's actually not always connected. So we use a Wi-Fi antenna. The drone is in the air. We send the signal up to the computer and tell it to start collecting data. it just goes off and does its own thing and stores it all in onboard memory, because processing that data and trying to get it back is a huge issue. So it's unfortunately not the best purpose for that.
You mentioned earlier some of the software tools that you had been using both to program the drone, but then also for processing the data. And Adam had a question about whether you were using in-house workflows when processing those, or do you just follow kind of the published workflows when you're doing that post-processing?
I'd say that when we started here, we originally followed a workflow that was provided by Phoenix, which is the company that built this drone for us, essentially. Phoenix Lidar, formerly California, and now they're down in Austin, I believe. I'd say that software changed over time, and so did the steps, and so did some of the use cases. A lot of these consumers are more interested in industrial needs, and they don't need it for science, right? Mm-hmm. So we kind of modified itself over time, and it's now to the point where we mostly use an in-house workflow, I think, that I've developed over the years, and we've shared it actually elsewhere. I've created a how-to guide and whatnot, but I think a good first step is on the Phoenix website. They do have a video guide to post-processing workflow. So on the Phoenix website, if you go to post-processing tutorials, they have a pretty good starting spot. Great. Other than that, if people are looking to get stuff set up, feel free to reach out to me and I'll talk your ear off.
Yeah, I think we're going to have to leave it there. I know we weren't able to get to all the questions in the Q&A, but yeah, I would encourage folks to contact Harrison directly if you have a question that either we didn't get to or maybe you didn't even have a chance to ask it. Please feel free to contact him directly, and we'll include your name and contact info in the description for this video as it gets posted on YouTube as well. So thanks again, Harrison, for a fabulous talk. Really cool work that you guys are doing there. And we appreciate you sharing it with us.
Hey, thank you so much. I appreciate the opportunity and the great questions. And like I said, it's a group effort. So I'm just happy to be working with a great group of people. And, doing the science is fun, but sharing it's also fun.
Thanks again.
Take care.